Structures and types of solids. We're going to classify solids into two categories according to how they're arranged. Our first type of solid is called an amorphous solid. And when we look at amorphous solids, they have considerable disorder in their structure. So in other words, they lack a long-range order in the way that their atoms are arranged. And a good example would be a glass liquid that's frozen into place. The second type of solid are your crystalline solids. And unlike amorphous solids, crystalline solids have highly regularly arranged particles in their structure. They're crystals at the microscopic level. So how are they crystals? Well, when we look at crystalline solids, they're made up of what are referred to as a lattice. It's a three-dimensional system of points indicating the position of the ions, atoms, or molecules that make up the substance. And when we look at this lattice structure, we want to consider what's called a unit cell. And a unit cell is the smallest repeating pattern of a lattice, and it would extend in all directions throughout the structure. So let's look at this particular diagram here. We don't need to get into too much of the specifics, but if we look over on the left-hand side, it shows us three different types of unit cells. And notice that the atoms are arranged in a little bit of a different order when we look at the three different types of unit cells that are pictured here. And then when those unit cells are put together in repeating units, we have what's referred to as our lattice, and that lattice structure is what gives us those crystalline solids. And again, there are lots of different types of unit cells that make up the lattice of a crystalline solid. We don't need to know them, I just want to just show you a couple of examples. We do want to talk about the types of crystalline solids. And it's easy for us to classify them based on what's at the lattice point of our unit cells of these particular crystalline solids. So we have three types of crystalline solids. Our first type are what we call atomic solids. And it pretty much tells you what's going to be at the lattice points, atoms. So when we look at atomic solids, they're substances that have atoms at their lattice point. A good example would be carbon in the form of graphite or diamond. Boron, silicon, and all metals are also considered to be atomic solids because they have atoms at their lattice points. The second type of crystalline solid is called an ionic solid. And again, the name pretty much tells you what's at the lattice points. Ionic solids have ions at their lattice points. Sodium chloride is a good example of this. So if we were to look at our model up on top for sodium chloride, we have sodium ions and chloride ions that are found at the lattice points of each of our individual unit cells. And the third type of crystalline solid is called a molecular solid. And again, the name implies that we have molecules at the lattice points. So molecular solids have discrete covalently bonded molecules at their lattice points. A good example is ice. So again, if we look at the illustration up on top, at each of our lattice points, instead of having atoms or ions, we have discrete water molecules. And those water molecules are held together by those intermolecular hydrogen bonds that we've talked about. So now we want to look specifically at atomic solids, and there are three types of atomic solids. We have metallic solids, which means that the atoms at our lattice points are metals, and they're characterized by delocalized, non-directional, covalent bonding between those metallic atoms. Our second type of atomic solid are called network solids. And in this case, the atoms have strong directional covalent bonding that lead to a giant molecule, sometimes referred to as a network. And our third type of atomic solid are called our group 8 solids. Now we remember that group 8 are our noble gases, but there is an attraction between those atoms which can convert the gas to a liquid to a solid. And we talked about those London dispersion forces, those weak intermolecular forces that can hold those particles together as a solid. So we want to talk specifically about an atomic solid which has metal atoms at its lattice points, or we want to talk about metals. And when we deal with metals, we know several characteristics about metals. We know that metals have high thermal conductivity, high electrical conductivity. They're malleable, which means that we can pound them out into thin sheets like aluminum foil. And they're ductile, which means that we can stretch them out into wires, like copper wire in your house. And all of these properties of metals are due to the non-directional covalent bonding that hold the atoms together in our substance. So we want to deal with how these metal atoms are bonded together. So we'll talk about the bonding models for metals. And when we talk about the characteristics of metals, they can be explained by these types of metallic bonds, which indicates that the bonding is strong and non-directional. And basically what that means is it's difficult to separate the atoms, but it's easy to move them around within our structure. So if we were to look at this, this is an example of our metallic model. And sometimes it's referred to as an electron C model. And basically what we have in this particular model are our metal cations are found within a sea of electrons. The electrons have the ability to move around, which explains the conductivity of metals. And the cations are free to move around, which helps us to explain the ductility and the malleability of metals. Now we want to deal with alloys. And alloys are substances that contain mixtures of elements with metallic properties. And there are two types of alloys, depending on how the individual particles are arranged in the substance. Our first type of alloy is called a substitutional alloy. And you see the word substitute in there. Substitutional alloys are ones in which some of the host metal atoms within our sample are replaced with other types of metal atoms. And those metal atoms that do the replacing have to be similar in size so they fit in and replace the host metal atoms. Brass is an example of a substitutional alloy. It's made up of 1/3 of its copper atoms that have been replaced with zinc atoms. Pewter is another example of a substitutional alloy. And it's made up of 85% tin, 7% copper, 6% bismuth, and 2% astatine. Our second type of alloy is called an interstitial alloy. And the term interstitial means between. So when we look at interstitial alloys, they're formed when some of the holes between the metal atoms are occupied by smaller atoms. And a good example of an interstitial alloy is steel. Steel is made up of metal atoms of iron, and within the spaces between those iron atoms, carbon atoms are filled in. So if we look here, we have two models of our substitutional alloys and our interstitial alloys. Up along the top, we've got a model of what brass would look like, where we're replacing some of the copper atoms with zinc atoms. And down on the bottom, we have a model of what steel would look like, where we have our iron atoms, and in the spaces between the iron atoms, we have carbon atoms.